Hey guys, welcome back. We are now in week 10, final week of the quarter, right? And then we have finals next week. So on the bright side, right, we're almost done with OChem. Tomorrow's the very last lecture. Going to be the last time you guys are going to see this stuff, hopefully. So it's something nice to look forward to. But I also know that this is also a stressful time because you're finishing out all your classes. And especially with OChem, there's so much stuff, so much material. So don't worry, we'll get through this together. This should be the second to last video that I'll probably ever make, just because I think they're still amino acids. So unfortunately not the last one, but I'll probably make amino acids tomorrow. I just need to make sure you guys aren't covering this here, Clayson. So someone just let me know. Actually, I'll probably know by the time someone actually watches this video. So I'll know if you need to know Clayson or not, but I don't think so, because normally you learn it before amino acids. Yeah, normally learn it before that, but I think she's going to skip it because there's just no time in the class left. So no worries. That's just great because it means that's less material you have to cover. So there's going to be this video, which is on carboxylic derivatives, and then amino acids, and we should be done for the quarter forever. But with that being said, again, a lot of information in this material, a lot of material in this course. So I know a lot of you might be worried, but don't worry. There's a lot of support coming your guys' way. On Sunday, we have a plan, or at least I currently have a plan to have a live Zoom meeting. Whoa, come and meet the gym, right? So if you want to come, even if you want to just come and hang out, that's totally fine. No big deal. But you can come and chat. The plan currently is to just go through the final exam. That's currently the plan. So we'll be covering that, and kind of use that as like a gauge of what to know, what not to know, or not what not to know, but you get what I mean. Come and we'll do that. Usually on Sundays afternoons, like 6 or 7. That's what I'm aiming for, because then at that point, I don't really have a time constraint. I'm not really I don't have to only be there for a certain amount of time. I can be there for quite a while. So it's okay if this goes pretty long, like 3 hours or something. No big deal. I could record it. That's probably a thing. I'll have to think about it though, because recording course material is always like a bit of an iffy thing. But I guess as long as you guys don't say anything, I won't say anything either. So probably will be recorded, just in case any of you can't make it. And I don't want to exclude any of you guys from doing that. But I am aware that you guys have a lot of stuff, right? Like on Saturday, I think I heard a TA is meeting with you guys, and then Sunday is with me, and then Monday you guys meet with Dr. Levens. So a lot of opportunities to catch up on material, or at least remind yourselves of the core concepts. So don't be afraid, right? There is time, there are resources that you can use to at least maximize your ability to pass this class, okay? Because that's the goal, is to pass the class, right? That's what we want to do. Yeah, cool. All right. Well, that's something to look forward to, and I'm very much looking forward to that as well. So we'll have some fun on Sunday. But with that, let's just get right into it. For the penultimate video, we're going to be talking about carboxylic acid derivatives. And so the previous video, right, or kind of before the previous, or not the previous, sorry, but a while back, we talked about ketones and aldehydes. Right? And so a big thing with these guys is that when we do reactions with ketones and aldehydes, right, let's say we add some kind of nucleophile, right, the nucleophile forms that tetrahedral intermediate. For example, like with a ketone, forms tetrahedral intermediate, and this tetrahedral intermediate is fairly stable, right? Despite the fact that O- wants to come down to reform the carbonyl, it can't really kick off any of the R groups, right? R's are terrible leaving groups. Carbon's not a leaving group at all. On the other hand, we could kick off the nucleophile, but that's just going backwards, right? That doesn't accomplish anything. So generally speaking, this tetrahedral is stable, and subsequent protonation captures this alcohol species. And so a majority of the ketone aldehyde reactions we called nucleophilic acyl additions, because we were just adding nucleophiles to the carbonyl. Now, obviously, for a majority of these, we continue to transform, but the main important thing was that we were adding to the carbonyl, right? We were not necessarily substituting. Well, with this new section of material, carboxylic acid derivatives, every derivative has what we call an X group or a Y group. The name kind of changes, but we have some X group. And if we choose our nucleophile very carefully, right, when we form the tetrahedral intermediate, okay, with our, I'll keep X here actually. I'll put R here, right? When O minus is in this tetrahedral intermediate and it swings down, right? Again, R is not going to leave, because if it does that, that's just very bad. R is just never inclined to leave. Nuke could leave, right? But that just goes backwards and that doesn't really help us. But now we have an X group. And this X group, depending on the derivative, can be a very good leaving group or an okay leaving group. Okay. Essentially, we've now provided the molecule with the ability to push something off as a leaving group. And with that, we can effectively substitute on that X group position. So now with these derivatives, we can do nucleophilic acyl substitutions where we can substitute X for some nucleophile as long as we're clever about what that nucleophile is, or if we're clever with what X is, okay? There's kind of two general rule of thumbs here, okay? Or really just one, but we can kind of separate them into two to understand this, okay? One good rule of thumb is that if X is a really good leaving group, so if it's a really, really, really good leaving group, for example, like a halogen, then virtually almost every single nucleophile, right, no matter how weak or how strong, is going to be able to substitute this X position. Okay, so this reaction works pretty well, as long as X is a really good leaving group, right? Because if it's a really good leaving group, it wants to leave, right? It can take electrons, right? Because it's going to leave as X minus, right? Another way of saying this is that it's a very acidic group. Okay, so it's a very acidic group. On the other hand, right, another way to kind of force this reaction to happen is to say that the nuke is a very strong base, right? Because if you think about it, when O minus is here and it has the decision, not really a decision, but imagine if it were able to decide, right? If it had the decision to kick off the X or the nu, or the nuke, right? When O minus swings down, again, we want to kick off the very acidic group. If the nucleophile has equal acidity to X, right? So it's equally a good leaving group, then there's going to be a lot of competition, a lot of reversibility. This reaction is not going to work very well. On the other hand, if the nuke is a very strong base, then the nuke is there to stay. It's never going to leave, right? I mean, if it's a strong base, again, strong bases are not good leaving groups. They're just good nucleophiles. So much more motivation to kick off that X group to allow that substitution to happen. Okay. So carboxylic acid derivatives, all of them are going to have some X group next to the carbonyl, right? Some are very great, some not so very great. And we have some tricks to kind of push the reaction forward. But the general idea is that the nuke is typically a stronger base than the X group, or the X group is just a very good leaving group, right? And again, the halogen, absolutely the best, and we'll talk about it. But if we're going to talk about the derivatives of a carboxylic acid, we've got to talk about the carboxylic acid first, the parent of the family. Okay, so carboxylic acids, what are these guys, right? Well, as the name suggests, these guys are acids. If you see there's an alcohol located right next to a carbonyl, I guess the closest thing to this is probably an alcohol, right? We talked about these before, right? Alcohols, they can lose a proton. But, this isn't that crazy acidic. It's usually around 15 pKa, which if you think about the pH scale, 15 is in the basic side of the pH scale, right? So this is still pretty basic. It's not that stable. And I mean, relatively speaking to most things, it is stable, but not that stable, right? It's not crazy stable. So usually to deprotonate these, you need some pretty strong bases like NaH, NaNH2, right? Even R minus, like the strongest bases in the world if you really have to, you can do that, but not that you have to, right? But generally speaking, the point here is that you need a strong base to deprotonate an alcohol. Carboxylic acids, on the other hand, when you deprotonate them, so we lose the proton on that oxygen, right? That oxygen is located that oxygen anion is located right next to a pi bond. And anions next to pi bonds like to resonate. So we can see here that effectively this O minus is actually split into two, right? Sort of like a schizophrenic anion, right? It's two of these oxygens that are holding the minus charge. The charge is very balanced across two electronegative atoms. So this balancing of the anion, right, makes the anion more stable, especially on these two electronegative atoms, right? Very, very good. So when we think about how acidic the carboxylic acid is, I mean, it's in the name, right? So it's got to be some level of an acid, and it's fairly acidic. It's around 5, the pKa for carboxylic acid. So, 10 doesn't seem like a big difference, but you have to remember this is 10 to the 10. So that's 10 with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 zeros. What even is this number? It's like 100, is that trillion, right? 1,000, million, billion, trillion. Yeah, so 100 trillion times more acidic. That's a lot of O's, right? It's a lot of O's right there, or zeros. Okay, so carboxylic acid is incredibly more acidic. A wide variety of bases can now deprotonate this carboxylic acid. And not only a wide variety, but milder bases as well. So for example, we can use things like NaHCO3 or bicarbonate. Right? Bicarbonate's a very mild base that can deprotonate a carboxylic acid. Cannot deprotonate alcohol, by the way. So you need strong bases for this. So usually like very uncomfortable situations you have to be in, right, to deprotonate these, but you can use a weaker base here. Really the star of deprotonating a carboxylic acid is the amine family. So whether you have RNH2, R2NH, or even R3N, right, amines actually can deprotonate carboxylic acids, which make, for a very, this is very synthetically useful. These are milder conditions. Okay, but again, very, very acidic creatures, these carboxylic acids. Now, really, the value can vary from like 3 to 5. And usually what will depend on whether it's closer to 3 versus 5 is, what kind of species is attached to the carboxylic acid. So maybe you might remember, it's okay if you don't, but like in acidity, if I have like a positive charge located near a minus charge, that usually increases acidity. So if there's some group here that increases positivity, then this is a more acidic compound. For example, let's say that I had this here, this trifluoromethyl acetic acid, or TFA, trifluoroacetic acid, TFAA, I guess you call it too. But this is very, very acidic, very close. I think it's actually even lower than 3. I don't remember the exact value off the top of my head, and neither should you, right? You should just have a general feeling for where this thing is. Okay. I guess something closer to 5 would have to be something with like a donor group on it. Something that's making for a more negative experience. And so negative, that's not very good, right? So, acetic acid is a good example of this. Acetic acid donates a little bit. So this is closer to like 4. I guess if I wanted to even make it worse, I could do something like this, put like an ester kind of thing going on there. But this species here, at least, to me, this looks like this would just like spontaneously just like explode or something. This is not very stable. So if it existed, right, it would probably be close to 5, not very acidic at all. But just things to think about, right, in terms of what makes for acidic or not acidic things. Okay, cool. So carboxylic acids, right? These guys are primarily acids. And so when we think about trying to do these reactions with nucleophiles, right, where the nucleophile adds into the carbonyl, right, and essentially substitutes out, right, we would hope that it's very clean cut like that the nuke just adds, and then we kind of kick some group off and we, call it a day. But again, carboxylic acids are acids, and a majority of nucleophiles are actually strong bases. For example, a very common nucleophile is an amine. And we just talked about on the other slide, amines like to deprotonate carboxylic acids. So what you'll actually form instead are these carboxylate salts. So we'll get this here. You can even see this with other nucleophiles as well, like RO minus, right? Deprotonation on that position there. This will not really give a salt, but it'll give an alcohol and a carboxylate, right? What's another good nucleophile you might see in this class? I guess if you guys remember, this is okay if you don't, but oops, sorry. I like hydrides as well. right? If you guys remember, that's okay if you don't, we'll talk about it anyways. But hydrides, right, also have a hard time with these transformations. Okay. But carboxylates as as an electrophile are not very electrophilic. All these species here are particularly stable. So when it comes to the reaction of carboxylic acid with nucleophiles, it's pretty darn difficult to do. There are not very many nucleophiles out there that can accomplish this reaction. So if we're going to do any kind of substitution reaction, we got to get a little clever with the acids. Everything else, don't worry. The derivatives are very clean cut. They do what you want to do. It's just the carboxylic acids that are a little bit picky because they can form this very stable carboxylate form, and not very many things are, strong or big enough to, challenge the carboxylate system. Okay, so actually, we'll say though, I think I mentioned it here, despite the fact that these are stable electrophiles, so they're not very willing to do substitution on themselves, they are very, okay nucleophiles. So for example, let's say that I had a carboxylate and I have, let's say like an RX, I can actually get a pretty fairly good SN2 reaction here. If any of you guys need sort of like a parallel, this is sort of like Williamson ether synthesis, right? You guys might remember you have an alcohol and you do NaH and RX, where RX is primary, and you can add on that R group, right, to make an asymmetric ether. You can do the same thing with carboxylic acid, right? Except you don't really need a very powerful base here, because again, milder, stronger acid, milder condition. So you can use something like pyridine. You'll see this a lot. That just looks like this, right? Hey, look, aromatic compounds. Things are starting to come together, right? All those things we've been learning throughout the quarter. But you can use a mild base. That'll just deprotonate here, form the carboxylate, right? And the carboxylate will just do SN2. So bad electrophiles, but they can get by as nucleophiles. So I guess there's some nice part to that. Okay. But what are some ways that we can trick a carboxylic acid into becoming an electrophile? Well, one of the things we can do is introduce some inorganic reagent. Very popular one is like PBr3 or SOCl2. We can look at both of them. But how does this work? Well, carboxylic acid is a nucleophile, right? Better nucleophile than is an electrophile. And PBr3 has 3 of these bromides on it, makes it very, very electrophilic. So when we have these two species next to each other, you can imagine phosphorus with 3 bromides, very electrophilic. Carboxylic acid decides to attack. Now, here's an interesting thing. A lot of you might be enticed to go ahead and do this, right? Because we know there's an alcohol, and that's willing to attack electrophiles, right? Not a bad idea. But remember, the oxygen here has lone pairs next to a pi bond. I guess if you needed a parallel to make here, the parallel you want to make is to an enol. When we had enols, right, we never really attacked with the oxygen lone pair, right? It was that the oxygen sent electrons into the pi bond, and the pi bond is what attacked. Okay, so if this is how our enol system works, and the only difference is, enol versus carboxylic acid, it's just that there's an oxygen, right, instead of a carbon, right? Not much is different. It's just that we're going to attack with the pi bond. So actually, instead of attacking directly with the alcohol, we go ahead and, instead of doing that, right, we actually attack with the pi bond. Oops, there we go. And so what we get out, one of these phosphoruses will leave. Okay, but what we get out is the structure here, which kind of looks a little nasty, but it's okay. Okay. And so if we kind of redraw this, it's kind of not sitting very weirdly, right? What we get out is a structure here. Okay. And so now we've added the PBr3 onto the carboxylate. And in a sense, right, we have first off removed that crazy OH that deprotonates whenever it can. So we've removed the acidic portion of the carboxylic acid. And on the other hand, we've also created a fairly good leaving group. Okay, turns out that this PBr2, OPBRT is a fairly good leaving group. Okay, Okay, so it's a fairly good leaving group. So when that bromide that we just kicked off is floating in solution, goes ahead and attacks at this carbon center, right? Makes sense, right? It's a protonated center, so it's a bit more reactive. Okay, so we had it on. And again, when we break that carbonyl, right, we break this carbonyl, oxygen is going to go ahead and swing its electron lone pair down and it has to kick someone off, right? Again, we're not going to kick off the bromide. If we do that, we just went back in time, right? We went back a step. That's not what we want to do. What we want to do is kick that new leaving group that we made, that X group, so that we effectively get a substitution. Okay? We have now successfully substituted the OH for the Br. Okay, so that's great. Great news, right? We've managed to get rid of the oxygen there. So again, this is one of those mechs that's a little more challenging. It's a little more on the challenging side of things, but follows a general pattern, right, of having some X group that effectively gets kicked off. Oops. Yeah, that effectively gets kicked off by that oxygen lone pair. Okay, so that we can get a substitution on that center. And so here, after something deprotonates this, right, we form what we call an acyl bromide or acyl halide, which is one of the family members of the carboxylic acid. It's one of the children that we'll be discussing how to react in just a second, or not a second, but in a little bit. Okay, cool. So this is one way we can trick a carboxylic acid into doing what we want it to do, which is really nice. Okay, no need to worry about any acid bases, right? Because again, we effectively, by adding this electrophile, get rid of that OH that was such an issue earlier. You can also use SOCl2, or this is also another reagent. Right? And so it sort of follows the same mechanics where we attack the sulfur. Depending on mechanisms, sometimes you'll see this quick up. I've recently read somewhere that it's actually more likely to be an SN2 type attack, so that's what I'll teach you guys. But you can actually go ahead and attack and displace, again forming something like this. Okay. And so once again, that chlorine that's floating in space will just go ahead and attack here. And we'll get out something that looks like this. If you want to, if any of you want to impress Dr. Levens or your TA that grades this, if this is your mechanism, you can actually do something really cool here. If you draw it particularly like this, if you want to show the decomposition, rather than showing it as this lone pair kicks down and kicks off this leaving group, right? Because now we've made this particularly good leaving group, we transformed it. What you can do is this, actually. You can use the chlorine to attack the hydrogen. So chlorine can attack the hydrogen. That OH bond electrons come here, and then we go ahead and we kick off the oxygen leaving group like that. So if you look, it's kind of has like a cyclic sort of a cyclic six-membered transition where electrons are moving in a circle. Hey, that looks kind of familiar. That looks like benzene. This is actually what we would call like an aromatic transition state. So it's actually very favorable. Happens very, very quickly and irreversibly, I might add. But this gives out to us, well, if I draw exactly what it will look like, it'll look like this. But if I want to turn it over, right, I can do that. It'll do this. Okay. Again, something in solution will just, oh wait, sorry, never mind. This was picked up, so we don't have to worry about that. Yeah, so make an acyl halide. Okay, cool. So this here, I know this mechanism might look a little crazy, especially since there's two different, right? So I'll kind of try to separate them. But again, try to look for the pattern, right? This is probably the most complicated, easiest to put on a note card, right? And just kind of forget about it, but it follows the pattern. It just uses that extra step of getting rid of that, acidic group that's kind of an annoyance, and making a very good leaving group that we can go ahead and substitute out and form a new family member. Okay, cool. So carboxylic acids can become acyl halides. Very, very easy reaction. Okay. Now we kind of talked about this on the other page, but we can use the basic form of a carboxylic acid to make what we call esters, right? Which are, instead of having an OH group, we have an OR group. And so the way this would work, right, again, is you, that first step, let's actually write this stepwise so you guys can see this. Okay, we can take off that proton there. And then we can add an RX group that we do essentially like a Williamson ether on. Although it's an ester, so it's like a Williamson ester, I guess. But this forms what we call an ester functional group, and that's totally possible. But there's also a way to do this in an acidic fashion, in a way that doesn't require to use the carboxylate if you don't want to do that. And so all that does is all I really do here is we use alcohol and we use an acid instead. Okay. Now, again, I have a nucleophile and I have an electrophile. And as we saw, carboxylic acids aren't bad nucleophiles, right? They're very, very good at attacking electrophiles. So we can go ahead and we can activate this position here. Yeah. Again, it'll form something like this, but if you want to, you can always draw it the other way around. Like that. A lot of you probably thinking, dude, why not just do this, right? Why not just attack like that? It looks like that's all it's doing. That is true, but you always want to be as correct as possible so that no one can will actually you when they're grading your quiz. So technically, this is the most correct way to do it, but you can also just draw it like this. That's totally fine. Okay, but hey, we have an activated carbonyl. Yeah, and so this carbonyl can go ahead and get attacked by ROH. Now, ROH is not a strong base at all. That's why we're not really too worried that there's this free alcohol group here. It's totally fine. The free alcohol doesn't interfere at all. No base whatsoever. So the alcohol goes ahead and attacks in. So we get this here. Okay. Now something in solution will pick this proton up. So we'll get to here. Okay, cool. Now again, oxygen could make a choice here, right? Could usually make a choice where it kind of swings down the lone pair and kicks off a group. But if I kicked off either of these groups, whether OH or OR, let's say we just kick off the OH, right? I'm effectively using an OH minus leading group, which, I mean, we're in acidic conditions here. So OH minus doesn't really make sense, right? Because OH minus is a base. So one thing you guys have to start to build in these acid and base reactions is, does my charge make sense, right? Or does my group that I'm using make sense? If I'm in acidic conditions, I should never see OH minus, right? Because OH minus is a base, right? That would never make sense in an acidic condition. So don't kick off OH minus here, right? Kick off another type of group, right? Or try to transform it into a group that makes more sense in acid. A general good rule of thumb that I would recommend is that if you're going to do an acidic reaction, you should mainly have positive charges. Okay, mainly positive charges, positive and neutral. If you find yourself drawing positive or neutral charges, you'll be fine. Right? Basic conditions though have minus charges in them. Okay, so just something to keep in mind, just to build that intuition, so your mechanism work is easier. But anyways, obviously not going to be able to kick off that group just quite yet, right? Because we're going to form that OH minus, which is a little iffy. But that proton that we took off the alcohol, right, that could go on the OH. And that forms a positive charge, which that's totally acceptable. And so now when this O minus swings down, go ahead and kick off that water. Because then again, anytime you form water, you want it to leave. And what we get out is our ester. Again, something in solution, probably even that water we just kicked off will probably deprotonate that ester there. Okay, but what we get out is the ester molecule. Cool. So again, we can do this in basic condition where we deprotonate and then we do an SN2 type attack. That totally works. But we can also make use of our acyl substitution mechanism by just doing this in acid. That way we don't have to worry about, again, that OH getting deprotonated and kind of ruining the reaction. Now, one interesting thing to think about is, well, what's really the driving force of this reaction? Because when I get to this point here, right, when I get to the tetrahedral, where OH can choose to kick off OH, right, or OR, it seems like those groups are very similar, right? OH is, OH like H2O versus like ROH. I mean, there's not much of a difference there. And that is true. There really isn't that much of a difference. So generally speaking, this reaction normally has absolutely no driving force. If I don't do anything to modify this reaction, like usually, this is very, very reversible, very, very reversible. So what we say is that at stoichiometric equivalence, right? So 1-to-1, nothing really happens here. But a way to kind of trick the molecule into accepting the alcohol and kicking out the water is to do two things, right? One is just heat it, right? If you heat it, you're dehydrating the system, so you're pulling out water from the system. The other thing is to use a lot, so an excess of the alcohol. If you flood the system with alcohol, right, the system has got to use it, right? That's just Le Chatelier's from Gen Chem, if you remember that. Okay. So usually the rule of thumb, at least that I learned, is that you use about 3 equivalents of alcohol for every 1 equivalent of the carboxylic acid. That's what really pushes this forward. But you've always got to use this at a high equivalence or excess, okay? You cannot do this at stoichiometric or 1-to-1. Why am I bothering you guys with this? This could be a very good vocab question. Okay, so let's put stoichio. So stoichio, like stoichiometry, right? 1-to-1, it's not going to work. You've really got to push this reaction forward. And so this is something that's, we'll come back to this for esters. This is usually a problem with esters as well. But as we'll see with acyl halide, it's not a big deal because acyl halides are usually very reactive. Okay, so first example of where we see, hey, sometimes our reactions need a little bit of help. How can we do that? We just throw in extra alcohol, heat it up a little bit, and we see the magic happen. There's actually a name for this. I believe this is the Fischer esterification. I might be wrong, actually. I always forget which esterification the Fischer is. I think it's this one, though. Middle mini rant. I hate these name reactions so much because, what does Fischer even mean other than a name, right? Dude already has projections. He has a synthesis. He has so much going for him, and you have to just put his name on a reaction too, right? A lot of these guys just have egos, right? Actually, speaking of egos, there's this guy, E.J. Corey. Oh my God. Any of you interested, just look up E.J. Corey and look at how many reactions he has. There are a lot of stories that this guy's just like stolen reactions. He has his name in like 100 reactions. Like there's so many Corey blank reactions, like Corey Fux, Corey Tchaikovsky, Corey. Okay, so that's kind of funny. I can't even remember half of them. There's so many of them, though. If you look up Corey reactions on Google. Oh, Corey Seaback, Corey Johnson. There's so many Corey reactions. It's like, dude really just put his name on everything. So anyways, my little rant about egos in chemistry, right? But yeah, anyways, cool. Now, one last thing before we move on from this, right? This mechanism that we see in acid catalysis, right? This is a very generic mechanism. So the next time we see an acid catalyzed reaction, right? Whether it's with a carboxylic acid or maybe something that's similar to a carboxylic acid, like, hint with an ester, the arrows are wildly going to be the same, right? With the protonation, the attack, proton transfer, and then the elimination. Okay, so get used to seeing that again, seeing those patterns. This is really going to help you out. Okay, cool. All right, so we can turn carboxylic acids into esters, and it's usually not a very hard reaction to do. It's usually fine. Okay, cool. All right. Now, the last thing that we can turn a carboxylic acid into, kind of, is an amide. But this reaction, it's kind of an interesting one. So let's say that I have this here. So an ammonia, for example. This reaction sucks. Okay. Now, what do I mean by it sucks? Well, hopefully some of you are shaking your head in disbelief because there's something we went over earlier as to what amines like to do with carboxylic acids, right? First and foremost, amines are bases. And so really what's going to happen here is you make an ammonium salt. So really the most thermodynamic answer here is that we want a salt up here. Okay. So for a long time, this is a salt. But if you heat this for a couple days, just kind of funny, I'm saying a couple days, right? You can eventually get this to reverse, and then it'll push towards the amide product. So this is a very good industrial scale reaction where if you imagine industrial reactor, you have a big vat, right? Which is full of just carboxylic acid and amine. You just heat it, right? Just put it on a burner. Right. So you just kind of like put it on a burner or something. Let's just put like a little fire down here. Right. So we got a fire. And you can wait. I mean, industrial wise, like you can wait years, months, like have a long time, right? Eventually, like this will make a lot of amids, but on the lab scale, on the, organic chem scale, on your scale of like where we need something within a day, this is a very bad reaction to do. It's not very advisable. It's not the best at all. So generally speaking, amids are a bit inaccessible from the carboxylic acid, but there is a little trick you can do. And kind of, I guess we're going through the first reaction of the derivative family, but you can actually turn this into an acyl halide and then react this with an amine. And this is generally the more acceptable approach to making amids. This is a very good approach. Okay. So carboxylic acid to amide, possible, just not in one step, right? No one's really got the time to like sit there for days waiting for their amide to couple to their carboxylic acid. Okay. Kind of looks like a imagine like a little diving board here. Actually, wait. I guess this could be like a person, right? This would be like a person here about to dive in, right? Something like that. Anyways, cool. All right. So that being said, carboxylic acids, a couple of different things we can turn them into. We can turn them into acyl halides, right? That's just via SlCl2 or like the phosphorus variants, so PbR3. Just remember that this will just turn into a bromide, not a halide. Or sorry, not a chloride. So I guess I'll just put X here just to be very generic. Right? We can depronate them and then add Rx to do like a Williamson ether type reaction to make an ester. Or we can add this an acid, right, in heat, right? So excess in heat. And so what we'll get is the same sort of result, right? This is the Fischer esterification. And if we were industry chemists, process chemists, right, people with industrial reactors, we could do the amide reaction, but really we should be doing it from here. Okay, and so we can make amides, right, kind of through kind of an extra step, but we can kind of do that. So these are the reactions of the carboxylic acid. And hey, look at that. These are our family members, right? We have a acyl halide family member, we have ester family member, and then the amide family member. Okay. Now, before we tie the ribbon on this, before we end on the carboxylic acid, there is just one more type of reaction we can talk about, and that's just a redox reaction. There is one type of redox reaction that works on carboxylic acids. It is the lithium aluminum hydride reaction. You don't need to know how, I don't think you need to know how this works, but all I would really worry about this is, again, so carboxylic acid can react with strong bases. Lithium aluminum hydride is no exception to this. So very first thing that happens is the acid base. But it turns out lithium aluminum hydride is that kid from high school that you haven't seen in years, who spent all their time at the gym, and now you finally see them and they're this like huge ripped person. They're incredibly ripped. They have 6-pack abs. They have, like cannons for arms, right? Absolutely ripped, absolute meathead, right? Absolute unit. Okay, this is what lithium aluminum hydride is. And turns out they weren't really happy about that joke you made that one time in high school. And if they come to get revenge on you for it, okay? And you're this, you're this just really weak carboxylic acid in comparison to this guy. So, it's time for lunch and all you've really been packed is a knuckle sandwich, okay? But turns out lithium hydride is the one thing that can punch through a carboxylic acid, right? The carboxylic acid isn't, resilient to everything. And eventually this will reduce down into an alcohol. Well, first it'll reduce into alkoxide, and then, the water in the second step will just turn this into an alcohol. A way to think about this is that you're just essentially erasing the carbonyl. Okay, you're just getting your, absolutely decimated. Okay, so yeah, so just be careful, right? Just keep that one in mind. Lithium nitrate just kind of punches the hell out of everything. It's a super, super reducer. So we can make alcohols with this. Okay, cool. All right, so those are the reactions of a carboxylic acid. And really, these reactions were meant to kind of convey, hey, we can turn this guy into a bunch of its family members, a bunch of its children. Okay. So now, actually, we're making very good time right now. Now all we have to talk about is the individual reactions of all these derivatives. But before we do that, there's one thing we should discuss, and that's just the general reactivity pattern or general, qualities of the family members. So we have the acyl halide, we have the ester, and then we have the amide. Okay. Now, despite the fact that these guys are all family members, right, there are certain things that makes them different, right? That's why they're different molecules. And so, in my opinion, if you can remember one thing about the three of these, right, that makes them different, you can remember a lot of things about these, because there's one trend that if you understand it, you understand a million different other trends because they all kind of fit in together. Okay. And that is their resonance trend. Okay. So kind of talked about this with the carboxylic acid, right? But the carboxylic acid, what makes its conjugate base so stable is the fact that there is a lone pair. You can form a lone pair, put a lone pair next to a pi bond, right? Well, if we look at all these derivatives also have lone pairs next to the pi bond. So the question becomes, how much can these atoms resonate with that pi bond? How stable are the electrons next to that pi bond? Okay. When we think of, atoms we've talked about like oxygen and nitrogen, right? This just goes back to our acid-base trends. And if I see oxygen and nitrogen on the periodic table, right, we know oxygen's more electronegative, and hopefully remember that nitrogen is more basic. So with the added effect of being less electronegative and more basic, nitrogen is much more willing to donate its electrons to any species, especially if it's a carbonyl, right? So you can imagine an amide spends a lot of its time resonating with the carbonyl. Okay, so this is actually a very common resonance form. If you talk to some biochemists and even some organic chemists that are doing like biological work, a lot of them will argue that this is probably the most, accurate representation of an amide, that it spends practically all its time looking like this because it's just a very good, thing to do, is just to donate. Okay. On the other hand, oxygen can also donate, but it's a little more electronegative, right? It's less basic, a bit more electronegative, it's a bit more acidic. So this lone pair does donate. That's totally possible, but not to the same extent. Okay, so yeah, we do get a bit of donation, but not as much, right? It's there, but it's not as much. Okay. Now, we never really talked about halogens donating, not very much at least. We talked about it a little bit when we talked about aromatics, right? When we talked about, if there's a halide, right, sometimes it can donate in. The major thing to take away from that was that, halogens, if we think about them as a donor or a withdrawer, they're mainly withdrawing groups, especially chlorine. I mean, chlorine is in the third row, it's not in the second row, so, some kind of advanced stuff. But if we think about the pi bond overlap between carbon and chlorine, right, that pi bond overlap is not very good. It's not amazing. So in terms of resonance, actually, I don't really think we would say this resonates at all. In fact, if we wanted to draw a resonance form, right, I wouldn't even draw one where the chlorine donates in because it's not a very common effect that we observe. If anything, right, chlorine is a withdrawer. It is ready to leave. So chlorine, instead of donating in, a common resonance form you might, maybe you guys won't see it, but higher classes would see this, is actually this here, where the chlorine is very much willing to depart. It's very much willing to leave, right? So it's actually already almost taking, this is almost like an ionic compound. Not exactly, it's more covalent still, but it's almost an ionic compound. this actually has a resonance form. Looks like this. So generally accepted, it's generally accepted that if anything, acyl chlorides look a bit more like this than they do like these guys. Okay. So in terms of resonance, right, if we look at the resonance trend, it's very much so that the amide is the most resonating of the derivatives, right? Chlorine being the least. And so if the amide is very willing to donate, right, into the carbonyl, it has a very nice pact with the carbonyl, right? It's very close sibling to the carbonyl. On the other hand, chlorine is already packed up and ready to leave. I mean, again, if you think about what is the most, one of the one of like an accepted resonance form that I just told you about, right? Chlorine is already on its own, so it's ready to leave. It wants to go to the to the other coast, live a new life, see new perspectives. So in terms of leaving group ability, right? I mean, we can also even see this, right? Chlorine, halogens, we've always learned are very good leaving groups. Nitrogens are always very bad. But in terms of leaving group ability, right? Chlorines are already on their way, or halogens are already on their way on leaving. So leaving group ability, right, kind of goes to the left here. Another way of saying that then is that the reactivity of the derivatives climbs towards the acyl halide. So reactivity is higher in the acyl halide than it is in the amide. Okay, amides are very, very resilient. As we'll see, they really can't do very many reactions, not very many at all. That's a good thing, right? Actually, think about that for a second. Why is it good that amides aren't very reactive? And I'll give you guys a little bit of a hint here, but we'll come back to this. But there's a very, very good reason why amides are not very reactive, or it's good that they're not very reactive. That's my one hint to you guys. Anyways. But yeah, acyl chlorides, very, very reactive. They definitely are ready to go ahead and leave. Okay, amides not so much. Now, I think at your guys' level, understanding these three trends are the most important. But it's still, I think, important and just safe to kind of cover some other trends, just in case, because you never know. And again, all this information is kind of just, you can extrapolate all this information just from the fact that there is a lot of resonance. Okay. But another trend we can kind of pull out, right? Another thing that we can kind of see is when we look at the resonance form, right? Again, all the electrons kind of, I mean, in the exception of the chloride, right? The electrons kind of pull on this oxygen. So there's an O minus, and O minuses are fairly, they're fairly good bases, right? So if we think about basicity of a derivative, right? How likely are these derivatives to grab a proton? Right. Again, part that's going to matter there is who is most willing to stay in this resonance form where the O minus is more prominent. So amides, who are mostly resonating, and again, if you ask most organic chemists or chemical biologists, they'll say that this is the best representation of an amide, right? Amides who spend a lot of time in this O minus form are going to be the most basic of the derivatives. So basicity increases this way. Okay, so amides, very, very basic creatures they are. Okay. And as we learned before, if something is basic, right, it makes it a very weak acid. So we can also get for free an acidity trend. Now, this acidity trend is not too important to understand. This is actually alpha acidity. So let's say that we had like an alpha proton here, right? That's kind of what we're referring to. But again, you guys are skipping ester enolates. And this is actually a bit more advanced than you would probably want to know. So not too big of a deal that we totally understand this. Okay. But hey, if you know what acidity is, it's not really hard to pull out what the basis trend or the other way around is. Okay, cool. So look at that. Just by knowing how a derivative resonates or how much it resonates, we can pull out all these trends for free. And so I will tell you that if you need to figure out a particular trend, right? If you need to figure out particularly if something, some kind of trend in the derivatives, just think about how resonance might affect that. Okay. Actually, a very beautiful example of this is, let's say you're just randomly asked, what's the boiling point? Like, who has the highest boiling point? Who has the lowest boiling point? Right. That's basically like, essentially asking you who has more or less intramolecular forces, right? Or who has, more or less stronger bonds, right? if we're asked about higher boiling point, right? Again, in order to boil something, you have to excite all the bonds, right, or all the potential bonds that there are in that molecule. As you can see in the amide, we have this extra, strong pi bond versus, here we have, just kind of this carbonyl that's already kind of weak because it lost its bond to the chlorine. So pretty easy to surmise that, hey, that amide with that really, extra strong pi bond, right, that's going to have a higher boiling point, right? And also, again, practically, if you think about it, right, why is it so good that amides have such a high boiling point? Well, if they didn't, we would just boil, right? We are all amides, right? All of us are amides. Our proteins are amides. So it's, if you want to, you can also think about things practically as well, right? I guess it would be really funny if on the quiz you had to figure out a trend and you just thought about how that applied to you, right? Like, again, if you thought about boiling point, I remember there was a student a long time ago for one of the 118 classes. She told me that the way she figured out the answer to, again, the boiling point question was she just thought, I'm here and I haven't boiled yet. I'm not a cloud of steam, right? So obviously amides have to have the highest boiling point. So funny little story that is. Okay. Cool. All right. So again, it's just some important trends to know and just some extra ones just in case, because you never really know. I guess one thing that might also help is to also kind of trace out the leaving groups here, because I kind of just said them. We didn't really talk about them, but Cl minus, right, or really X minus, OR minus, and then NH2 minus. Again, usually the quizzes and the finals can be a little pKa heavy, so just to know a pKa is just nice enough. Halides are usually negative numbers. It really just depends, but I guess a good negative number is like a -5. Actually, I like this one because we can say this is -5. This is about 15, and then this is about 35. Okay, so rough numbers, but they all kind of have the same, like they're all kind of the same, group of numbers, like 5, 15, 35. They all have fives in them, so it's not too bad to remember. I guess you can think of it as is it like a 20 difference? Does that work? I think it's like 20 in between each of them. So that's I guess a nice way to remember that. Okay, cool. Now, one little question that's usually asked in higher level classes, but again, I'm just going to incorporate it because it doesn't hurt to give you this information, is where do ketones and aldehydes kind of fall into this? They kind of fall in between here, where aldehydes are a bit more reactive than ketones, right? Why is it that, we have the ketones and the aldehydes falling up here? Well, remember, esters and amides have this resonating group that makes them a lot more stable, right? Less resistant to reaction. They're not really willing to leave, right? Ketones and aldehydes don't have that, right? That's how they're more similar to a chlorine. But chlorine, again, is a withdrawing group, as we talked about, right? It's ready to leave. H and R are not, really leaving groups, right? They're not ready to leave, but they are, more reactive than the ester and the amide. Okay, so that's where these guys usually fall. This is a nice little thing you can probably just draw on your note card. Okay, cool. All right, so that's a bit on the reactivity and the properties that we tend to see from the carboxylic acid derivatives. Oh, I guess carboxylic acids kind of fall around here with the ester, in case you need to know that. Okay. But let's go ahead and get the reactions. Like I mentioned a second ago, acyl halides are the most reactive. So we will see the most reactions with the acyl halide. We'll see a big drop off with the ester, and then practically nothing with the amide. So don't worry, it's not like we're going to do 20 reactions for each of them. It's more of we'll do a lot for acyl halides, and then ester and amides kind of have a couple of them. Okay, cool. But let's get into the acyl halides. So what can the acyl halide do? Well, again, this guy is the most reactive because if we just think about it, the halide is such a good leaving group that any nucleophile that we add to the system is usually a stronger base. And so when O- comes down, it'll usually always just kick off the Cl, and we'll get very clean substitutions. Okay, very, very clean. So what are some examples of nucleophiles that can do this? Well, we can always just add water. Right, there's water. Actually, acyl halides are so reactive, they'll react with the water, the moisture in the air. So usually when you do this chemistry, you have to do it inert. Do this chemistry inert because acyl halides are just so reactive, right? Imagine that, right? You've put acyl halide, or you've prepared acyl halide in your flask, and you leave it out for just 1 minute, and you start to see it start to change color or to turn to like a gunk. It's because it's reacting with the water in the air. Okay, but we can go ahead and add that on. Now, a lot of you might be tempted to go ahead and do a proton transfer here, which is totally fine if you want to do it. But again, acyl halides are so reactive, right? Chlorines are just very good leaving groups. So when minus comes down, or when this minus is present, it will just come down immediately and kick off Cl. So you're welcome to do a proton transfer. I'm aware that that's the way you learned it in class, but you can also just go ahead and kick that chlorine off, right? It's just so reactive. It will always do that. And then chlorine will go ahead and deprotonate that there. Okay. And so, what we'll get out is a carboxylic acid. Okay. So if an acyl halide wants to become an carboxylic acid, you just hydrolyze it, just throw in some water. Okay. We can then ask the question of what happens if I use organic water. And same kind of thing, right? Again, this guy will just pop on. If you want to, you can do a proton transfer. You don't have to. But what we get out is this ester here. And chlorine, we'll go ahead and deprotonate it. And we get out is an ester. HCl, okay? And then last but not least, right, we can use like an amine. Remember, this was that better way of making amides from carboxylic acids. But we can, I don't really want to, okay, I'll do it, whatever. I didn't really want to, but I think I should, just to. Minus comes down, kicks off the chlorine. And then the chlorine will go ahead and deprotonate that. And we get out an amide. Okay, cool. So again, acyl halides, fairly simple. You just kind of throw a nucleophile at it and it'll accept it and it'll go right on its way. Okay, substitutions are fairly simple with the chlorides. Super, super reactive, these guys. Actually, you can't really buy acyl halides. You have to kind of make them in the lab. So you make it on the spot and you react it on the spot because not very shelf stable. Again, these guys will react with the air. So very, very, very easy on decomposition. Now, one thing that maybe you guys didn't notice, which is okay because you guys are not chemists, right? But one thing you might notice here is that, forming HCl in these reactions. And HCl is a very toxic, byproduct that can kill you, right? That's not a good thing to have at all. So generally what will happen, or a way to kind of bypass this issue is you'll see that a lot of acyl halide reactions use pyridine, right? Pyridine is just it's an amine whose primary function is to act as a base. Another thing you'll usually see is T, triethylamine. Again, just a base. Amines that don't have protons on them, so like this nitrogen has no proton, this nitrogen has no proton. These kind of amines are very good bases. And what they'll just do is they'll just clean up this acid, just to make sure that you're not going to die. So, for example, like for this one, oops, sorry, not that, this. So we'll have this, or we'll have this. So just a very practical reason, right? You don't want to, accidentally, drown yourself in something very toxic. In the case of the amine, if the amine is like cheap, you can just use a lot of the amine and the amine will just like cancel out. So we'll have like stuff like this. If the amine is expensive, then you just, again, use pyridine, it's really cheap, or triethylamine is really cheap. It's not like that big of a deal. There's also like, you can also use hydroxides too, but just to kind of keep it consistent, just do this. Okay, so these like tertiary type amines are usually very good bases. There has been some investigation though into this, and it turns out that there's like a higher level effect also, but you guys don't need to know this. Is more of a 118 thing, but good enough that you guys know that you can use these guys as bases to kind of clean up the acid. Now, please keep this in mind, because if you look at these are organic byproducts, right? They're salts, but they're organic salts. So you can be required, or you may be required to also include them Okay, so don't forget those. If you see T or you see pyridine, right? So you can see this written as TA or as PYR, right? Consider that they might be cleaning up some acid and include them. Usually an important thing to do. Okay, cool. But acyl halides, very, very clean cut. They will just do the substitutions that you want. Okay, and these are majority of their reactions. Cool. Now, when we move on to the ester, again, ester is sort of just a, right? It's kind of like a carboxylic acid, but now we have an OR group. Again, esters are more resilient. If you go back here, acyl halides don't even resonate, so that carbonyl is not supported at all. Very, very reactive. Chlorine wants to leave. Oxygen, right? The introduction of an OR group, right? We do get a bit of donation, right? Not as much as the nitrogen, but there is still donation. So this oxygen is not ready to leave just quite yet, right? It's not, and it's not that much better of a leaving group, right? So with that, esters are a bit more resilient. Okay, a bit more resilient. And so doing these reactions usually takes some kind of catalysis. So let's say that I wanted to do, add water across or onto that derivative. You can't really do this reaction just with water. Nothing's really going to happen. So just NR. You have to introduce some kind of catalysis. So for example, some kind of like H+. Okay. Now just for the sake of time, because we're kind of really good on time and I kind of want to keep this short. I'll just go ahead and do this very quickly. But we can go ahead and pronate on the ester. If you want, you can also do the thing we did before. It just adds like, redrawing a kind of perspective, but whatever, no big deal. Right, nothing's really that different. But then water can go ahead and add. Actually, let's put this down here. Okay, but we get here, and then again, something in solution, we'll just pick up this proton. Okay, so we get to here. Okay, all right. Now this should feel very, very familiar, right? We did an acid catalyzed mechanism just a second ago, right, with the carboxylic acid. And this is also acid catalyzed mechanism. Guess what? Nothing's really that different. It's all the same arrows, just with different contexts, right? Different, different atoms or different parts of the molecule. So in the same way that we took off the proton from the nucleophile, we'll go ahead and add it back on to the X group. And then we'll go ahead and we'll kick off that X group. And something in solution picks up this H. And we get our carboxylic acid. Okay. So again, acid catalyzed, a lot of the arrows were the same, right? If I go back here. Yeah, a lot of the arrows are exactly the same. It's just a matter of context, right? What are we doing? If anything, this is almost like a reverse. It's almost a reverse of this reaction. So the Fischer esterification reverse is just adding water back in. Okay. Cool. And again, we can just quickly make sure, do my charges make sense, right? Building that intuition. What's allowed in an acidic reaction? This is totally allowed in an acidic reaction. Okay. Now, once again, that question of how good is this reaction? Not very, right? Because again, difference between an ester and a carboxylic acid, not that big. So how do we save this? Use a lot of water and we use heat. Again, esters are a bit resilient because of that potential resonance. So usually heat this up a little bit, watch it probably a long time as well, like maybe like an hour or two, right? But yeah, cool. So we can do acidic hydrolyses or, add water acidically across an ester. Okay. We can also do this reaction in base, which again, we couldn't do with the carboxylic acid. Because remember, carboxylic acids were a little resilient. If you use base, right, they turn into the carboxylate. But esters don't have that issue because again, they are OR groups, right? So, great for us. So we can go ahead and use some base as well. So base, right, it's usually strong enough to just attack. That's what we tend to see here. Oops, oh yeah. Oh, sorry, not OR, OH. So OH, just like that. And then, sorry, oh, that was fine. There we go. Okay, so we get the addition of the OH group in. Now here's where things get a little interesting and a bit tricky, right? Because again, if O- comes down, we kind of might feel uncomfortable here. Kicking off the other OR kind of leaves us with an OR minus group, which we talked about, not the greatest leaving group, not the best thing we can do, right? So the molecule might hesitate in doing this. But if I try to seek out a proton, I mean, this is basic condition. So there really isn't a proton to take out here. So how do we reconcile? What do we do? Well, it turns out that actually when O minus comes down, OR does fall off. So we do get OR minus. And so a lot of you might be feeling like, oh man, you just lied to me. You said we can't do that. Well, hold on a second, right? Because OR minus doesn't just leave without a little gift, right? It takes a little bit of payment in order for it to leave. And that payment is the proton on the carboxylic acid. Okay? So it turns out carboxylic acids will donate their proton to the leaving group so that that leaving group is happy to have left, right? It makes a weaker base. Okay, so it's kind of like a delayed proton transfer, right? Because if I did it here, or if I turn this into ORH plus, again, we're in basic condition and plus charges are not good, right? So we are eventually protonating the oxygen to make it a quote unquote good leaving group. It's just a little delayed. Okay, and so essentially this here is actually pretty irreversible. And that's kind of the driving force of this reaction. Okay, so carboxylic acids, or sorry, this here, it's not a carboxylic acid, it's a carboxylate. And it's what we'll see in these basic reactions, right? If we're in a basic solution and we're forming a carboxylic acid, really what we're going to form is a carboxylate. So just keep an eye out for that. Yeah, cool. Again, if we see another basic reaction, we might consider that this same kind of thing happens because, again, a lot of these reactions kind of fold over and doing the same thing. This mechanism is also pretty short too, so I've always, liked it. I've liked it quite a bit for, for quiz problems because you can, technically they're a little bit quicker, right? So cool. All right, so we can hydrolyze an acid, which kind of follows the esterification process we looked at earlier. We can also hydrolyze in base, right? And again, kind of doing something that's not so great, but doing something here that's not so great, but it's okay because we, make peace at the end. Yeah, cool. Now, with esters comes back an idea, right, that a lot of us, might have been a little uncomfortable with throughout the quarter, but, the more we see it, the better we feel, right? And that is intermolecular reactions or ring type reactions. So let's say that I have an ester that looks something like this, right? Or like an ester that looks something like this, right? So it doesn't matter the size of the ring, it just matters that it is a ring, right? Let's say that we have to do a mechanism for these, right? Again, just go with what you know, right? Do all the steps how you know it, right? Don't overthink it. Don't doubt yourself. Everything is still the same. Like let's say do the basic mechanism. Still the same. It's just, in the context of a ring. Oh, oops. I forgot the oxygen in here. Okay. So again, minus will come down. Again, we'll kick off this group here. And this is where people get a little tricky, kind of thrown off because they're like, how does this reconcile? Well, we for sure are going to make the ester here. And this oxygen is tethered. Oops, sorry. Oh, not OR. I apologize. Let's make this H. Okay, so 1, 2, 3, 4, 5, and then 6. Right. We have the oxygen tethered there. And again, this oxygen goes ahead into protonates. Again, that's sort of the driving force of this mechanism. Okay. So don't be afraid of rings, right? Don't be afraid of them. They're still doing the same thing as we saw in the mechanisms. Just keep in mind that everything is tethered together. Okay. I guess the way to think about it is, just breaking this here, right? I guess like a general mechanism for all of these acyl derivatives, right? Again, if all we're doing is replacing X with the nucleophile, just keep in mind that sometimes the nucleophile can just be tethered right to the molecule, right? Oops, sorry, not like that. I meant like this, right? Just like that. So this is like a general mechanism here for all acyl derivative reactions, right? All we're really doing is cutting on this bond here, right, to replace the X with the nucleophile, right? And sometimes that X group is just tethered to the original molecule. Okay, so don't be afraid of rings, right? Everything is still the same. You can also just very quickly look at the acid catalyzed mechanism here. Right, again, majority of it's quite exactly the same. I'm just going to be very quick about it. Just going to skip some steps. Just kind of drawing it to draw it. Yeah. So yeah, I already know people are going to ask, but just so you know, I am skipping steps here. I'm just going through this very quickly just to kind of get an idea that it's exactly the same arrow pushing. So for those of you that are, very, very, detail oriented and care about the mechanism a lot, which is totally fine. It's a good thing to, I'm a very mechanism person too. 1, 2, 3, 4, 5. Right. You can, as long as you know your arrow pushing, you can always quickly surmise what the answer is, even if you're not confident. Okay. So yeah, again, this was a very quickly done. Skipped us a couple steps here, but still got out an answer here. Okay, cool. So again, rings are going to be there. Don't be afraid of them. I guess this also works in the other way too, because actually technically Fisher esterification can also be like a ring type reaction, right? If you have an alcohol, right, that can go ahead and attack there, right? So actually maybe as practice, try to draw the mechanism of this, right? 2, 4, yeah, that'll work, right? Try to draw the mechanism of this, right? And how that would work. Okay, and again, don't overthink it. Just use what you know and you'll be fine. Okay, cool. All right. Now, if hydrolyses work, right, do reactions with organic water work? And the answer is yes. So here's where we have to get a little specific, but let's say that I have methyl acetate. So this here is methyl acetate. Okay. And I wanted to turn it into ethyl acetate. So where there's an ethyl here instead, I can totally do that. I've just got to add in, again, either acid or base and the corresponding alcohol. Now, we've now seen 2 acid mechanisms. It should not be too difficult to guess how this mechanism would work. So I would actually recommend pausing and trying this on your own. Okay, so if you want, you can do that. But I think at this point, you guys have the tools, right? You've seen it enough times that you can do it as well. Not that I'm not going to do it, I'm going to do it, but I think you should definitely, use this time to also try it on your own too. Okay. But again, I'll do this fairly quickly, but it's all the same thing. Or actually, sorry, let me do this here and then there we go. Do a proton transfer. This guy off. Acid mechanisms are usually the longest because there's so much proton transfer stuff going on, right? Pesky protons, right? They're making our lives so hard. But that's okay. The more and more you do this, the more, you can see how I can just do this in a minute, right? Because I've just done it so many times. So hopefully you guys can get to that point too. Just fix that off. And now we get is the ester. So this is ethyl acetate. Ethyl acetate is a very nice smelling. Generally speaking, esters are very nice smelling. Some esters smell great. Like mint is an ester. That's methyl salicylate, I believe. Should be this. I believe this is mint. Let me just make sure. Or not, it's spearmint. I forgot what it is. Salicylate. What is methyl salicylate? Did I just make that up? Okay, I think I might have made that up. Oh, wait, no. It's the wintergreen. That is mint. That is mint. Oh, sorry, it's not a methyl. It's not a methyl ether. It's this. But mint is an ester. It's a really nice smell. Bananas are an ester. I believe they're this one here. Bananas. But yeah, you can go online and find charts of this, but a lot of fruity smells. Oh, I was close. I was close. It's the other way around. Oops, not that. So this is this, and then it's like this. It's something like this, but that's banana. So bananas are an ester. I love bananas. What else is an ester? Actually, really funny. I think like the smell of wet goat is also an ester. So it's like the one like bad smelling ester. But yeah, I mean, you can go online, you can find everything. There's actually a guy I knew that he used to make esters in his garage, and he kind of went crazy making them. So take that as you will. But a lot of fruity smells, very nice smells. Vanilla is an ester, I believe. But yeah, esters are very good smells. But ethyl acetate, very great smell. Also, just a very good solvent as well, because again, it is not that reactive. So cool little thing there. Cool. All right. So this process here, where we turn one ester into another, we call transesterification. And once again, right, how good is this reaction? Not very. So we heat it and we use excess of the alcohol. Okay, just to push it to one side. I'll very quickly also just do the base version here. Base will also work. Again, the arrows for this one are so nice because it's very simple. Go ahead and kick that guy off. And voila. Now, this is the one thing that might upset you guys, which is totally fine. Why in the world is it okay to kick off the O- here and give it no reconciliation? It turns out, I mean, O- is not that bad of a leaving group, but yeah, this is one that's going to be a little iffy. And for the purposes of a video like this one, where I just want to get through it turbo quickly, we'll just have to accept it. It's okay to kick off the O- there. Oops, sorry, not that. This. Okay. Something in solution will probably protonate it, but yeah. But this is like one of those, like, you kind of just have to trust me on this one just to make things a little bit easier. Okay, cool. Now, the final reaction we can do with esters, right, is turn esters into amides. Okay, so we can turn esters into amides, and usually you do this in acid, which, guys, come on, acid. There's so many massive mechanisms. So it's great, right? Because it means that there's a lot of pattern recognition you can do, a lot of generic mechanism work. So again, I'll do this very, very quickly just because it's kind of just doing the same thing over and over and over again. But you can turn esters into amides. Bit of a hard reaction though. And I mean, again, esters are quite resilient. Just go through this a little quickly. You won't really see a basic version of this reaction, so there's not much to worry about there. You only really need to know that you can do this in acidic. Okay. Maybe we can make amides. Again, you can do this with ammonia, primary amides. It doesn't really matter, right? I just been using ammonia a lot just because it's kind of like the most basic amine. Okay, but there we go. All that'll do is just turn this into this. Again, how good is this reaction? Not very. So we'll use an excess of the amine, and we'll just throw this, just kind of boil this or reflux this just to get it to work. Okay, cool. So we can turn esters into amides. Now, one thing you'll notice is that we didn't really talk about turning esters into acyl halides, right? So, doing this reaction here. And so a great question is this possible? Well, if I kind of take the idea of like adding like Cl and adding an acid, right, we can kind of go through a mechanism for this, right? And I'll go through this a little bit fast, but you can imagine this gets protonated. And then the Cl minus can go ahead and add an attack, right? So we'll get to this here. And so, once we get to this point here, this might look kind of recognizable, right? This tetrahedral, where we have an O that's willing to swing down to like lone pair, an OR, and a Cl, right? That was kind of just the thing we saw back here with all the acyl halides. And in every single example, right? Whenever we had the Cl there, or any halide, for example, the oxygen lone pair was always willing to just swing down immediately because they got to kick off Cl. So Cl being such a reactive group makes it so that it's very difficult to add across or to substitute into an acyl derivative. In fact, you really can only make it from carboxylic acids. So the only way that you guys know how to make acyl halides is to use SOCl2 or PBr3, right, from a carboxylic acid. No other derivative is going to be capable of making an acyl halide, just because anytime you add Cl, it's just going to fall right off, right? That's why we have to do the whole trick, right? We have to trick the molecule a little bit to accept that halogen. Okay, so no funny business allowed with making halides for anything other than carboxylic acids. Okay, so unfortunately, that's just going to have to be the case there, but that's okay, right? That makes our life a little bit easier. One other thing, actually, before we move on, just like it's another fun fact, but esters, right? Esters are really biologically relevant. You guys did a lot of talking about this recently, though. So you guys know that, right? Our fats are esters, right? They're triglycerides kind of coupled to carboxylic acids. And a really neat thing is that if you hydrolyze these in base, right, you essentially make carboxylic or carboxylates, which are pretty good soaps, right? So the next time you want to impress someone, I guess you can tell them about this. Hey, if we took our fats, actually, this is a weird example, I know, but you know how in movies there's always talks of the acid vat, right? Like, ooh, the acid vat. Don't put your hand in it, right? The acid vat, it's bad for you. Actually, I don't really know why they call it an acid vat. I wonder if it's because acid has like hard tones in it, like the word acid, right? Like the duh sound. It's like a very hard sound, so it sounds like very scary. Acids aren't actually that bad. If anything, it's bases that are bad, right? A base bath is what should scare you, because if bases hydrolyze fats, right? Which, I mean, that's what they do, right? Imagine putting your hand in strong base. You're going to actually pull out a skeleton because it's just going to eat up everything, right? Because bases, they'll eat up the esters, right? Your fats will hydrolyze all of them, turn them into soaps, and you're just going to have soapy hands, right? Or literally soap for hands. So cool process, right? Saponification. So not that this is like advice. This is purely for educational purposes, but the more practical way of getting rid of a body is using base. It's not using acid. The movies have misled us all. Absolutely not at all what you want to do. Not that you want to do it at all, so you shouldn't be doing it at all. Okay. Cool. All right. So then all that leaves us with then is going to be the amide, which again is if the ester is resilient, the amide is incredibly resilient. So much so that you do any type of reaction with this, really, nothing's going to work. The amide cannot turn into any derivative. So acyl halide can become the ester or the amide, right? The ester can become the amide. The amide cannot become anyone. It can't do anything. Very, very resilient, right? It doesn't really do much. And so it's quite literally the least reactive kind of derivative we have. Although, again, that's a good thing because, again, we're all amides. And I'm happy that I don't just react with the air. That'd be a very terrible situation to be in. Okay. But one thing you can do is you can hydrolyze amides. You can do it in acid or base. Just, it takes a long time. For those of you that take biochem, you'll learn it. It'll make more sense when you learn this in biochem too. Like you'll get the perspective, right? But if any of you work in a bio lab, right, that works with proteins to kind of hydrolyze out individual amino acids, you literally leave something like I think it's the autoclave, but you literally just leave something heating, like a peptide heating in acid overnight. So you need almost 24 hours, almost 12 hours you need just to get anything from a peptide hydrolysis or an amide hydrolysis. So very, very, very difficult to do, but very possible. I mean, still possible, very extreme conditions. But again, acid mechanism, I'm going to go through this very, very quickly because we've been seeing this all night. Oops, sorry. Okay, H2O. That'd be positive. Again, we'll have a proton transfer. Now, this is probably the hardest step, right? The proton transfer and then the eventual kickoff of the nitrogen there. Again, nitrogen, worst leaving group out of all of them. I mean, if you think back to the pKa's, the N pK is very, very, very high. So it really, really, really does not want to leave. And for good reason, right? So again, it's very resilient. So it's a very, very hard step to do. Oops, sorry, why do I keep doing that? Okay, cool. So very, very quickly, that's just the acidic hydrolysis. Now, one thing that always kind of throws people off again, and something just to remember, is again, amines and carboxylic acids, amines like deprotonating them. So don't forget to don't forget to protonate your amines in acid, right? That's just what's going to happen. Since we're in acidic condition though, this carboxylic acid will get protonated anyways, because there's so much acid in solution, right? But in acidic conditions, right, your amines should be protonated, switch to your carboxylic acids, just how it works. Okay. You can imagine a basic version of this reaction as well if you wanted to. Again, a bit simpler. Although this is a tough one. Drawing this makes my heart hurt because it just, it doesn't make sense that this happens, right? But I mean, it's got to do it. Okay, but NH2 minus, oops, sorry, that should be this. Again, this is what makes it a bit irreversible. But you'll form carboxylate and amine. Okay. So amides, they can be hydrolyzed. Very, very, very difficult thing to do, but you can do it. And really that's it. That's the only reaction these guys can do. They can't do anything else. They are again resilient, and for good reason, right? They are the building blocks of life. You wouldn't want the building blocks of life to kind of break down to the moisture in the air, or otherwise every time someone coughed on you, you would just melt, right? We would just be puddles. And that would not be a very nice life to live, to be a puddle, right? Cool. So with that being said, that's the majority of the reactions. So great. I think we got that done in about an hour and a half. That's nice. I'm happy about that. That is the majority of the reactions of acyl derivatives. Again, just to kind of go over the key features, right? Right. Oh, actually, never mind. Thank God I went to this page. Thank you. Thank you, Jim. Thank you, Jim. This is a this is a Limothy. My older brother. Anyways, there is actually one more section we can cover, which is reductions. So we'll just cover that really quickly. Okay. Acyl halide reductions. Again, these guys are super, super reactive, so you can really use any reducing agent you want. It's not that big of a deal. Usually we'll offer a simpler reducing agent, like a borohydride. This is a weaker. Makes sense why I'm saying this in a second. Okay, but hydrides, right? I mean, H is essentially H minus. It's adding on. Okay, but again, minus comes down, kicks off the Cl without a doubt. And what we get is an aldehyde. Don't forget, there are 4 hydrides on one NABH4, and this is an aldehyde, and aldehydes also reduce. So you can imagine BH3, right, or another NABH4, doesn't matter. Both of these have the equivalent. It's no big deal. But this will actually just continue to reduce. So this will turn into a primary alcohol. Okay. This is kind of the feature with acyl halides. They just kind of overreact. Okay. You can also use lithium aluminum hydride. Again, this is just the puncher, stronger. You don't need to, but you can if you want to. And that will turn into an alcohol as well, primary alcohol as well. Okay. You can also add organometallics, which are just like RMGPR or RLI. And same kind of concepts, just R minus adding in. Right, come down, kick off the Cl. And what you get is a ketone. So right here, aldehyde. And you get a ketone, but same sort of idea, right? Ketones also react with Grignards. So another R minus will just add in. And what we get are symmetric tertiary alcohols. So symmetric tertiary alcohols. Okay. And so those are the reductions of an acyl halide. Pretty simple. The only other group that, again, I think you guys will cover reductions is esters. And esters kind of follow the same pattern. Okay. You have to use lithium alone hydride. NABH4 will not work. Okay, but this will work. And again, just to kind of go through this very quickly, you'll make an aldehyde, and then you'll make a primary alcohol. Okay. Again, this guy will just break the esters phase. So it's definitely going to work. NABH4 is a little bit cooler though. It's a little bit milder, doesn't have anger issues. Okay. Same thing with the organometallics, right? If I use RLI, you'll make a ketone, make a symmetric tertiary alcohol. Okay. So what I mean by symmetric tertiary alcohol, all that really means is that, if I kind of draw it this way, you can kind of see it, but we have two R groups, and then you can kind of ignore what's, originally on the ester, it doesn't really matter. But if we kind of draw a line down the middle, right, the left looks like the right. You might also remember that if there are two of the same group on the same carbon center, right, that carbon center has to be symmetric. And that's what happens, right, is we add two of these R groups, right, that makes a symmetric carbon center. Okay. Now, amides are very, very weird creatures. There's only one reduction you really need to know for these. Again, lithium hydride is what's going to be used to kind of break its face. But instead of turning into an alcohol, what happens is you turn into an amine. So you're essentially erasing the carbonyl. This is kind of reminiscent of how the carboxylic acid reduction works, right? Like if I want to visualize it, it's kind of just erasing the carbonyl. For the sake of time and just sake of simplicity, because I don't want you guys thinking too much, the reason why this happens is because the amide, it's again a very weird group, right? And it's such a bad leaving group that it kind of changes the chemistry. So it turns out that instead of NH2 leaving in the reduction mechanism, actually oxygen leaves as water, or kind of a water equivalent. Okay. And so because of that, we lose the ester instead of the nitrogen. Okay. Again, in the acyl halide, right, the chlorine, amazing leaving group, that'll pull right off. That's why we get the alcohol. And the ester, right, they're both oxygens. It just turns out the OR group is just slightly better at leaving. So that pulls off. We make the primary alcohol. In the amide, the carbonyl as water is a better leaving group, which is kind of crazy. So the amine kind of sticks around, doesn't really change anything. Yeah, cool. So the one reduction that's a little different, but visually very easy to understand, right? Not much to it. And you guys don't need to know mechanisms for that. I don't think so. So you should be fine. Okay, cool. But with that, that should be the end. That should be all we need to know for derivatives. If there was any confusion, please let me know. I probably might have missed one or two things, which is fine. But this section had to be rushed because you guys had to learn this all right at the end of the quarter. There's always something that gets skipped or something that gets rushed, and unfortunately had to be this stuff. Okay, cool. Again, think about the common feature. We went over like maybe 20 of these acid mechanisms that were all the same. They were all the same. So, think about those and how you can just kind of write one and generalize it over and over and over again, right? Don't do more work than you need to, right? And, kind of save on that note card space. Okay, cool. All right. By tomorrow, I should know what's left in the class. So I'll go ahead and make amino acids and kind of cover whatever's left. But hey, we're right there at the end. So, you should all be excited. I am too. Cool. All right. If any questions, please let me know. You guys have a good night.